Well, good afternoon. Well, thank you for being here. Been last session for the whole conference. I really appreciate it. Well, let me just do a quick self-introduction. My name is Kevin Liu. I am the lead PM for the SQL Server engine space. I have been with Microsoft for about 80 years, pretty much the whole time in the SQL Server engine area. And so today I'm going to talk to you about SQL Server 2014, which, by the way, just shipped this week, GA'd. And the most prominent feature in SQL Server 2014 is in-memory OLTP. So let's cover this subject. And I have roughly 30 slides, so it's a little bit tight. I'm going to run through the slides a little bit fast, relatively. You will have the slide to read offline. And also, I have several demos. You don't have to copy down any syntax. All the demo code is embedded in the slides, in the notes section. I have asked the event organizer to keep the notes, so you should be able to get all the sample code offline as well. So the agenda, I do want to talk about SQL Server 2014 OLTP quickly, and then look into in-memory improvements. There are several of them, not just in-memory OLTP. And then I want to talk about in-memory OLTP OLTP, architecture-wise. Then let's look at this from the developer angle. How do you implement a solution using this new technology? And of course, given the in-memory database, memory usage and control is a natural subject to cover a little bit. Data durability, well, it depends on the interest. I can skim through it. So the idea here is to just talk about the database durability nature, right? Even though it's in-memory database, there is really no data loss if you have a crash. So we'll talk about how we actually implement that. The last one, I think it's, if we have time, we'll cover a little bit. If we don't, that's OK. This is about the migration tools. I just want to introduce you to some of the existing tools you can use to get started with very low friction. So we got a full agenda. So here it's all up, SQL Server 2014. And there are multiple pillars for the release. The most important one is in-memory technology. That's the left pillar. And in addition to in-memory, there are additional other things we did in 2014. One, as you might know, in 2012, we have Always On, which is the HADR solution built into the database as the prominent driver for SQL 2012. There are some improvements in addition to that, but nothing really earth-shattering, right? So it's more like increasing the readable secondary from 4 to 8. If you have a readable secondary, if it's disconnected from the primary, in 2012, we actually don't allow you to do dirty reads, so to speak. But in 14, you're able to do that, right? It's a disconnected secondary, you can still do reads. Things like that. It's more like a top-level DCRs people ask for. Hybrid scenario, this one is a whole spectrum of options. The goal is to connect an on-premise server to the cloud. There are different ways you can do that. The most simple one and the non-intrusive one, of course, is you can push your backup to the cloud easily, right? So we added a backup to URL option. You can just push it transparently to the cloud. Run a readable secondary in the cloud. That's another option. So it's really a spectrum of options. So I'll just stop there on the 2014 broadly. And let's look at the in-memory technologies. In 2014, really there are 3 of them. The most important one, actually most of engineering effort went into the first one, which is in-memory OLTP. This is a relatively unique solution. I don't think we have a lot of competitors yet in the marketplace. And in-memory DW is something which is already in 2012, but it's not, maybe not widely used yet. The reason is this is the columnar index. Once you create the columnar index in 2012, it's no longer updatable. The whole table is locked, right? So it's not very useful for users. But in 2014, we allow you to update, right? So you still create a columnar index, the same performance for aggregate queries. Also, it's transparently updatable. And the last one is SSD buffer pool extension. So conceptually, this is very simple. This is about between memory used for the buffer pool and the spinning media. If you have some kind of a fast SSD device, like a PCIe-based device, you can introduce that as an intermediate memory hierarchy. Allow the clean pages to be destaged from the buffer pool into that cache. So this is very useful for traditional OLTP app, where you are having a lot of memory buffer pool pressure, but you don't want to spend the money to buy a lot of real memory. And this, by the way, is not compatible with eMemory OLTP, right? So that's quickly at a glance what the solutions are. For people who don't know OLTP versus DW very well, let me just say that OLTP is more a point lookup, point update, heavy contention, heavy concurrency kind of workload. And the DW workloads usually are large scans, very large aggregates, kind of analysis, decision support system queries. So they're very different query patterns. And indeed, we have different engine technology behind each of them. So the motivation, the motivation behind eMemory OLTP, why did we do it? Well, the market need is definitely one, right? When we talk about market need, there are really two parts to it. Usually people think about throughput, of course. Throughput is something people measure mostly, but also predictably low latency is another factor that's really important in the design here. And also people are very sensitive to cost. OLTP tuning is actually notoriously hard. It's actually very hard to tune. DW queries are easier, OLTP is not, right? And how do we achieve that goal for the market at low price point? The second one is maybe less apparent. The database engine, the core disk-based database engine, has been written about 15 to 20 years ago, right? And it has not really evolved drastically until now. So this eMemory OLTP engine is the first large-scale engine rewrite since about 15 years ago. Right, so the project started about 5 years ago and moved to the product group about 3 years ago. That's when I got involved. But you can see this is not an easy effort. Some people have the misconception to say, oh, is this just a DBCC pin table which you deprecated 10 years ago coming back? Well, it absolutely is not, right? If it's that easy, it wouldn't take us 5 years to build this. It's actually a really hard thing to do. That's why also you don't have a lot of competitors in the market at this stage. So, why did we rewrite it? The hardware trends, we'll talk about what they are, is, the way we designed databases 15 years ago, the premise for the hardware is fundamentally different today, right? So we'll talk about what they are. So essentially what eMemory OLTP is all about performance, right? It's not about a new language feature or anything like that. So it's all about performance. It's memory optimized, and it's built into SQL Server. That sounded very trivial, right? We come from SQL Server. Of course, it's built into SQL Server, but it's not so. The integrated engine approach is almost like, do you design an electrical car with electrical engine, or you build a hybrid engine? If you want to build a hybrid engine with gasoline and electrical, the transference of the power is actually quite complicated. So by building into SQL Server, we actually delay the release maybe by 2 years because of the complexity, right? We'll talk about what's the customer benefit too. And the last one, of course, is the due to the hardware reasons. So let's talk about the hardware reasons really quick. Memory, of course, right? In memory database, you can totally see, I'm going to show you the memory price point reduction over the years. Well, I'm not going to elaborate on that. Suffice to say, 1 gig now, depending on the DIMM size, is $10 to $20 per gig. It's really, when people say memory is still very expensive, it's relative, right? The other two hardware trends that's not very apparent when you think about your memory database, I want to call out. One is the CPU clock rate has stalled. So if you look at the graph, the dark blue graph, since 2003, we all know that the CPU clock rate stalled around 3 gigahertz for various reasons, right? And this is not a good thing, right? From the database perspective, we do benchmark all the time. Before, if we don't do anything, we rerun the same server year after year on the new hardware, the benchmark goes higher. Well, that free ride is over. What do we do, right? This is a negative factor. But the reason that the hardware vendors don't build that is because of, let's say, heat reasons, etc. They do follow the Moore's law, more or less, by build out, right? There is a heavy scale out inside the CPU. And a commodity server today, you can easily have 16 logical or 16 physical cores, 32 logical cores. And that's a commodity mid-range server. And database, even though it has inherent good concurrency design, 15 years ago, it was never designed for that level of concurrency, right? So the logs, latches, all those concepts become a problem. We have to rethink, how do we get around that? So this is a relatively dense slide. Don't try to race through the details. I will just talk about what the idea is and highlight one or two things in each of the columns. So the bottom are the drivers, why we do certain things, right? The top are the customer benefits. The middle is what we do as the core engine design. So the first column is about, well, memory is available, what do you do? Well, let's start with why did SQL Server or any database server have a page concept, right? SQL happens to use 8K pages. Why do you evolve data structure around 8K pages? That was never designed for in-memory processing speed. It's all for I/O transfers, right? You have a disk, that's a block device. You have to transfer to and from the disk very efficiently. Hence, you build a block addressable kind of structure to do that. Actually, when you do data manipulation in pages, it's very inefficient. You do page splits, the way you structure the data inside, you do row offsets, it's actually not very efficient. So the assumption here is, why do we design that way? Let's throw away the concept, say the data must live, a concept of the I/O transfer, and assume the data must live in memory, then all those constraints go away. So this is not about forcing the data to stay in memory, but it's about if the data is going to be in memory, what would you do to design the data so that it's most optimal for in-memory processing? So you can think about this almost as if you want to design a cache, right, data cache, you will never design with an 8K page boundary. So that's exactly what we did. This is almost as lightweight as a data cache. That's the easy part. The hard part is how do you expose the full ER model and the T-SQL surface area above the cache and have the full database ACID properties below the cache, right? That's the hard part. But that's all there, right? So including, for example, I said ACID. That's the D is durability for the database world. And let's say you run in memory, you pull the plug. Any committed transaction will guarantee when the database recovers, it's going to be there, even though it's in memory. So there is a full durability angle to this. So the second column is about, as I said, the CPU clock rate stalled. What do you do? The work we did here is, some of you may not know that SQL Server, after you have the query plan, the physical plan, we will interpret the plan to execute, right? So literally the data comes from the bottom of the query plan and then goes through all the parts, nodes of the tree. All those work is interpreted execution. So there is inherent inefficiency in the interpretation. So we force the new, essentially we rewrote the query execution engine, and there is no interpretation, it's all natively compiled. So the table itself become a callback, a natively compiled callback, and the queries or store procedures are essentially a tiny program after compilation. So then we run native speed without being hindered by the interpretation. So this gives you very fast business logic processing. Just put things into perspective. If you have business control logic, like a loop or some kind of condition check, natively compiled store procedure on a no payload condition will run maybe 50 to 100 times faster compared to a regular store procedure, right? The third column is about scale out. A lot of the concepts we had before, such as locks and latches, spin locks, super latches, all those concepts, they all went away in the new world. So we have a multi-version optimistic concurrency control that doesn't take any locks or latches. But still, I want to emphasize that there is still data protection. So when we do critical updates that different threads indeed contend on, we use a Windows low-level primitive called interlocked compare exchange, which really runs at 10 to 20 CPU cycles per protected update. In comparison, a lock or a latch can take 1,000 or several thousands of CPU cycles. So that's where the efficiency comes in when you have scale up, right? Let's say you move to a bigger server with more cores, or you scale out your mid-tier. SQL Server today does really well until you reach that, knee, and it usually starts scaling down, actually, as you add more threads. So the knee can be somewhere around 10, 16 threads, usually. But, what we have observed is with the new in-memory OLTP, you don't have that knee, at least in the mid-range server that we have tested. So what you get is really frictionless linear scaling. The last one, as I said, is built into SQL Server. So the best way to think about this, there are two parts. At the engine level, think about this almost like a hybrid car. There are two parts of the data management system that built in such a way that you can cross-collaborate between the two engines, and I will show you how that's done. And also all the tooling, surface area, anything you know about SQL, you don't have to relearn anything, right? Everything applies. Like HADR, language, management tooling, everything is the same. So before I go any further, let me do a quick demo of what do you get in the end, more from the business and user perspective instead of the technical angle. We'll have plenty of technical angle discussion, but let me show you what the app will get in the end. Okay, so this is a quick simulation of a e-commerce site. So on the site sells video games, and the right side is a load simulator. And let me start the load. So what it measures is this, the transaction throughput on the purchases, and also when the user pick a product, we do a several hundred parameter type of calculation to say, based on the user's profile and other reasons, factors, what's the recommended items given the user look at this, what's the other things we recommend to you. So the recommendation latency is the bottom. So it's you can see it's roughly 5.6 seconds, and the transaction is roughly 1,000 concurrent transaction. Well, that's the business perspective. What's the user experience? Let's try to click one. So you can see the bottom, that's the recommendation engine I just talked about. It does the store procedure calculation. It takes about 6 seconds. It's pretty long and not very friendly. And if you want to purchase an item, and because of the contention, it takes about 3-4 seconds. So here I'm just going to do a little bit hand waving. And by the way, everything running here is real load. It's not just facade. So when I transfer the table, contention table, to the in-memory OLTP, you get a 25x, not 25%, but 25 times throughput from the business angle, okay? And then if I natively compile the store procedure, let's see what the average runtime will be. So what it does in the background is simply drop the store procedure, recreate it, and the same thing for the table as well. And you get 8x. So what's the user experience? Let's try again. So you can see the recommendation calculates in a, thank you. And also the purchase is like fraction of a second, right? So the contention is gone. So there is no, it's not a facade, right? This is a real application running. All the delay before was due to real contention in the system. So this is a little bit hand waving, right? You know, but I will show you what happens behind the scene as well. Well, this is, you know, in a very simple example, I think you should realize two things. One is from the business perspective, on the same hardware, without rewriting the app. Actually, in this case, I didn't even shut down the app, right? The driver still keep on running. The app didn't really stop. So it's the same app. Somehow at the database layer, I did a little bit move around, you know, different table and store procedures. You get this kind of business angle improvement, but also the user experience improved, right, on the latency angle. User doesn't care about your throughput. They care about their own experience. So that you get a very good experience as well. So that's the business angle and the user angle of what you get using the database in-memory OLTP. So let's talk a little bit about how does this work in the engine level. So this is a architecture diagram of the SQL Server as is, right? Without in-memory OLTP. Most people, I think, are familiar with what I'm talking about here. The different stack, buffer pool, transaction log, data checkpoint files. So all those you are familiar with. So how does in-memory OLTP come into the picture? So let's assume you have 3 tables and 3 corresponding indexes in this picture. And we want to move T1 and T2 into in-memory OLTP. So first realize that in-memory OLTP is not an additional binary. It's actually built into SQL Server. As a matter of fact, when you install SQL Server, you don't even see an option to install in-memory OLTP. It's just there, right? It's built in. So when you run the in-memory OLTP engine, the memory space is declared under the same SQL Server EXE from the same memory manager, but we allocate large pages. And at the bottom, we have a checkpoint file. It's nothing more than a file stream under the scene. The reason we need this is we don't do random IOs anymore. We only do sequential IOs for durability. So this is actually a very good news. Sequential IO, you know, depends on what hardware you use. If you have high-speed SAS drives, you don't have to necessarily move to SSD to achieve very high throughput for sequential IO. So once you move the T1 and T2, declare them as in-memory tables, they disappear from the traditional buffer pool. They disappear from the traditional checkpoint files. One thing you may have noticed is the table operation is still logged, right, for durability reasons. However, index operations are not logged. So this is really important. Not only index is not logged, it doesn't get checkpointed either. There is no physical footprint for indexes. This is really important because, you know, people usually have a, you know, let's say a high load system. You have one table, you may have 10 indexes. The index, you know, change or the logging and checkpoint from the indexes can actually be much more than the data itself. It's very, very expensive to maintain them. So people do all sorts of tricks, right? They drop the index to do certain workload and put the index back on. And also index have tons of issues with defragging, all those issues. All those things go away. The concept doesn't even exist anymore. So the indexes are automatically built when data is being inserted or upon recovery, automatically rebuilt. And there is no fragmentation issue. So a lot of the old concept for DBAs is no longer applicable. And developers, actually, you care even less about that. So it's very developer friendly. You don't have to worry about those, I would say, convoluted DBA subjects. Yeah. So how do you access those tables? So this is where it becomes interesting between the engines. I said it's a hybrid engine. Well, if you are familiar with SQL Server or any database engine, there are usually 2 layers of the engine. We call a storage engine that manipulates the data at the basic level, and then you have a relational engine, which is figuring out the plan, execution plan, all those things, query optimizer, et cetera. So what we're trying to do here is called query interop. Essentially, you treat the in-memory tables just as if they were regular SQL tables, no difference. So you just insert, delete, update, whatever you want to do, you know, as if they're regular tables. So this is essentially combining the existing SQL Server's relational engine with the new storage engine. We kind of did a cross-shimming together, right? So this is good performance, but the benefit is also it's a very low barrier for adoption, right? Literally, you define the table, and your app will just run as is. But this is not the fastest route. The fastest route is where the native compilation also comes into play. So here you see on the left side, this is where we also replace the execution engine with a new execution engine. So now you have a full stack running in the maximum speed as possible. And a small sidebar note is you can declare the table as non-durable. So if you don't do that, by default, everything is durable. So you incur the checkpoint and the logging overhead. But if you declare the table as non-durable, we will not have any I/O for those table operations. And of course, you put a plug, the table recovers, will be empty, right? But this is a very powerful situation, though, scenario, though. People can use this as a relational cache, if you like, right? And literally, it's a relational cache. You can query the cache. It's high performance, just like your own cache. I don't think you can necessarily write a cache much more efficient than this, but you get all the benefit of transactional isolation, entity relationship, all those good things coming out of it for free. But it doesn't have durability. The performance actually usually we see depends on the I/O bottleneck. Usually give you like 2x on top of what you already have. So how does the performance work? So the core engine piece, I'm circling the new relational and the storage engine. The engine is maybe 20 to 40 times more efficient. So now a row operation usually goes down to about roughly 50 microseconds level, right? So it's extremely fast engine. However, give you a balanced view, the TDS stack has now been optimized. If your app is very chatty, you treat the database engine as a very simple singleton row retrieval and update, well, the overhead is high. So just give you a relative number. If you, even with a memory pipe connection on the local server, you do a single round trip through the TDS layer, it's usually about 300 microseconds. So it's 5 times more than, 6 times more expensive than the core engine piece. So you can see the inefficiency start to come in. And also, if your app today is heavily bottlenecked on I/O, well, if you still want to have durability, I/O is much, much slower than anything we just talked about here, right? I/O trip can take you up to 1 millisecond easily. So that can be a bottleneck. And one more thing I talked about is the new I/O for including log and checkpoint, they're both sequential I/O. So hackathon, by the way, I use the word hackathon. It's a code name. It's a Greek word for 100. So that's the internal code name for in-memory OLTP. That's a design philosophy, say, how do we achieve 100x improvement, which turned out to be too hard to achieve, at least for this go-around. That means you have to throw away 99% of the execution overhead. That's too much, right? But that's the aspiration. By the way, I'm just saying hackathon or the in-memory OLTP, all the I/O is all sequential I/O. There is no random I/O. So this is a early customer test showed that the gain is really a range between 2 to 25x. So if your app has been designed to have more business logic in the database layer, instead of treating the database as a very simple raw store, you actually benefit more. This is a very simple principle, right? You want to move processing closer to the data. The more you can do that, the more engine can do for you, the database engine can do for you. If you treat the database as a lightweight, point lookup only, there is not much we can do for you, right? So if you take advantage more of the database server, you can get 25x. But TPCC, or a workload derived from TPCC here, is actually the worst scenario. If you think about something which has been tuning for 20 years, we get roughly 2x. So this is more I/O bottlenecked, not really built for in-memory at all, right? So let's talk about next how to use from the developer perspective. So this is a new created table, DDL. And you can see there are quite a few things that's looking a little bit different. Let me just walk through one by one. First, the keyword is the table has memory optimized on. So this is the most important statement, that you declare this table is using the new engine. And if you don't specify durability, it's automatically schema and data, means the both durable. Schema only is the non-durable version I talked about before. We have two types of indexes. Here I'm just showing the hash index. This is a little bit more complex compared to SQL Server before. SQL before had only one index, right? Just index. But now we have two types of index. Hash index, you have to specify for this go around, this release, you have to specify the bucket count. So this is the same as you define a hash table. And usually it's roughly 2x size of the number of unique key value of the indexed column. And you also can define another type of index, second type, which is non-clustered parentheses range index. You don't specify the keyword range, but the intention is for range lookup. So the difference, I will talk a little bit more later. Hash is more for point lookup, very fast. One size of operation, order of one operation, you get to the row. Range is for a range scan. Hash is actually not very good for scanning, but range is. It's different purposes. Okay, so data format. This looks different from the page, right? There is no page anymore. So literally, a row is a floating row in memory. And you have some headers, overhead here. I think you add them up. It's 24 bytes plus 8 pointers. So allow up to 8 indexes for V1. So that's the fixed overhead. And then you have the payload. And so the beginning timestamp, end timestamp, all those things are for multi-version control. In other words, we never update the row in place. It's always a versioned. So how do you actually organize the data? You have to have at least one index, right? You can't have floating rows sitting in memory. We can't navigate through. So at least you have to have one index defined, and we essentially structure the rows together with the index. And there are two types of indexes. One is hash, one is the keyword non-clustered range index. So as I said before, think about hash as a point lookup tool and range as a scanning tool. You can actually define them. If you can't make up your mind, you can define the same two indexes on the same column. That's OK. And the range index, you don't have to specify any parameter. And I will show you the data structure in a minute. So this is a hash index. You can see logically now you have a structure to tie the rows together. And the hash index in this case is on the hash is on the name. And imagine you have a transaction coming in. MVCC, by the way, means multi-versioned concurrency control. You have a transaction coming in. The timestamp determines the visibility of the row, of course, right? And if you do an update, we simply untimestamp the first original row and chain them up. If rechain them, and if the earliest transaction in the system passes 100, that means that 50 to 100 timestamp is no longer visible to anybody. Then we can garbage collect it, right? We can remove that row safely from the system. So here it actually reflects a very simple design, but reflects an important concept, which is the database now is almost performing like a regular cache. But functionally, we build it rich, just like a database, right? So this is a perfect example for that philosophy. So I talked about hash index, and this is the range index. It looks like a B tree, doesn't it, right? But it's quite different from B tree. The internal tree structure is what we call a BW tree. All the node update is never in place. So you can see a lot of subtle differences with the regular B tree. And it's all updated with multi-version as well. But you can consider this as a higher performance B tree, if you like. But give you the range lookup, right? Let's say you want to scan from this date to this date, a narrow range. And with hash index, actually, you're forced to do a table scan, right? Because you can't narrow down the range. But here, we actually can be smart enough to scan a very narrow range. So for natively compiled store procedures, so that's the new syntax. Again, looks a little bit alien. Let me walk through some of the keywords here. Natively compilation, this is telling the system, well, compile this. Schema binding, this is to ensure stability, right? You can see the philosophy here is we're pushing a lot of work at the compile time, etc., and putting some constraints on, so at runtime, we don't do the dynamic checking, right? So the principle is important because, how often in a real high-performance OLTP system, you dynamically change your schema, right? But we just enforce those concepts so that the engine can run faster. Execute security context for the same reason. So here it's a little bit new, right? We're introducing the concept to say the whole section for the store procedure is atomic unit. And also the isolation level, the error language or the interpretation for the, let's say, dates, etc., parsing language you use, all those are fixed at compile time, right? The principle, as I said, is do a little bit more work at a compile time. It runs a little bit longer, but execution time is a lot more efficient. So there are two ways to access the optimized tables, as I discussed in the architecture diagram. So one is on the left side is the interop mode. Interop mode is virtually all full T-SQL surface area is supported. There is very little incompatibility, so to speak. But the performance is not the maximum, right? Sometimes we see 3x, sometimes we see 5x, so it's more like on the lower end of the performance gains. On the right side is where you combine both the fast execution, the query execution engine and also the access methods layer, right? Storage engine and execution engine together. So that's the fast path. However, there is some drawbacks there, right? It does require a little bit more rewrite, right? What I just pointed out before. And also the T-SQL surface area is not fully compatible because essentially we're rebuilding the whole query execution engine. It's very expensive for us. Join is supported, but auto join is not, right? So that's just one of the catches. Suffice to say, for the next version, we will plug all those important holes. The goal is when you identify the tables and store procedure you want to move, we want to make it as easy as a header change, right? And you don't have to modify the syntax internally. So let me show you a quick demo of a very simple example. You can see this almost as a mini version of the demo, the fancier demo I just showed you, but you can see behind the scene how the code works and how it performs. Okay. So as I said, don't worry about writing down the code. All this code is, by the way, in the notes section of the slides. You can read them offline. So here, I don't have a database. I will just create a regular SQL database. Okay. And then, and the file group. This has nothing to do with application. It's just generic thing you do so that you have a place for the in-memory OLTP to send the checkpoint data and use the new database. Okay. So now let's create a regular SQL table and have a store procedure to dump data into it as a baseline. I don't have any table. Let me just create the table here. And you see it's just 4 columns, pretty simple. Create a regular index on top of it. Don't have a store procedure. Let me just create a store procedure which does a loop insert. Okay, let's run this. Insert 100,000 rows. Okay. Well, you are just looking. This is a server, pretty simple box with 8 physical cores. And so this query takes about 12 seconds. Okay, you can just do a count. 100,000 is there, nothing fancy there. Let's look at the in-memory portion equivalent. Okay, so in memory here, you can see a couple keywords are slightly different. I did define a bucket count here, labeled as memory optimized on. I didn't specify durability, so it's fully durable. And I create a almost identical store procedure as the other one, but with a couple more keywords. you can see the natively compilation does take a little bit longer, right, for the store procedure to be created. So there are some creation time overhead. No. So now, let me execute this store procedure. Done. Literally, it's that fast. Thank you. Just to show you the data actually got in there, it's the same thing, right? Select. I'm treating the table as if it's a regular table, right? I didn't do any special syntax. So this is the interop mode of accessing. The insert indeed was natively compiled, but what I'm just doing here is nothing, right? It's just interop, kind of the more expensive way of accessing the tables. So that's it, for the simple way to use it. You see the syntax, and the barrier of entry to start with is actually quite low. So let's talk about memory consumption. So how do you know how much memory you're going to use? Assume when we say we will compare with SQL performance, we have to keep in mind we're always comparing in a fair way. We never compare with SQL when the SQL data is cold, right? The SQL is retrieving, or the traditional SQL is retrieving from the disk, then we are fully warmed up in memory. That's not fair. So the comparison has always been, when we say 20x, 10x, is always with the traditional SQL or another database fully warmed up in the buffer pool, right? The data is all there, and how fast you can process the data. So the memory usage for in-memory OLTP is actually quite frugal, right? There is a little bit of overhead. But if you think about in disk-based SQL, your pages, because of split reasons, right, and the padding, usually are half full, right? So you have half of the pages are wasted space in memory anyway. And we don't have that issue. And if you calculate that way, actually, the in-memory OLTP does not use more memory per se, and a lot of occasions when we look at the customer data, is actually even more efficient than traditional SQL in memory usage. So this is a very interesting thing now, right? People always have the conception to say, well, in-memory OLTP is more efficient because you use more memory. Well, not necessarily, right? It's a different design philosophy. We may use a little bit more memory, maybe use a little bit less memory, but that's actually not the determining factor. It's actually the design of leveraging the data being in memory, guaranteed you are much faster. It's not related to how much memory you use per se. So this is how you do the calculation. The header, we know the header size, 24, and essentially you can do, depending on the hash or range index, you can quickly do the calculation and figure out how much real memory you're going to use. And also, we have some reports to show you what the memory consumption is. Let me do a quick time check. I have 17 minutes. OK, let me maybe skip the demo for now and talk about, run through the key concepts. If I have time, we can come back and do the demo here. So the memory usage for in-memory OLTP is indeed a little bit more greedy than traditional SQL Server. Traditional SQL Server buffer pool, it's flexible, right? So if you're under memory pressure, you allow clean pages to be kicked out, or you do a checkpoint, you have a way to actually reduce the footprint, so to speak. In-memory OLTP does not allow that. We literally force you to keep the data in memory. If you keep inserting at a certain point, we'll actually put pressure on the rest of the system. And then we'll push buffer pool out. And if you physically run out of that, the system will crash. Right? So this is one thing that's important to know. So how do you deal with that? So the top section, we don't have to repeat that. Data has to be there all the time. The bottom part is the in-memory OLTP can be integrated with resource governor. So you can build a safe barrier to say, I want to define a dedicated resource pool, and my system, let's say I want to allocate 60% of my SQL Server memory to in-memory OLTP, but don't cross that boundary, because I allocated, I still have other workloads on traditional SQL tables. I want that part in buffer pool to be stable without being pressured by in-memory OLTP. So you can do that pretty easily. And then in-memory OLTP will bump against it, but it will be smart enough to leave enough margin that if you indeed have insert failures, you can unwind yourself. You can actually do deletion, etc., unwind yourself down. But in the meantime, the other workloads, like reporting workloads, non-in-memory OLTP workloads, will not be interfered. So that's the design here. Okay. So this is the demo. I think I will skip for now because we only have 15 minutes. And also, I want to leave a little bit of time for Q&A. By the way, this is the last session. I can stay as long as you guys want afterwards to do some Q&A as well. So the last part I want to talk about maybe a little bit less concern to the developers, but more for the DBAs. How do you actually achieve durability? So this is important in the sense that you should have the confidence to know that even though it's in memory database, it doesn't mean it's volatile like DRAM, right? The durability is built in. So the way, other than the logging, we also have checkpoint files. The checkpoint is essentially a dump of the current state without you to replay the data from the log from the beginning of history, right? So the checkpoint in memory OLTP, you have a data file and data file. That's how we achieve only sequential I/O, no random I/O. So you can think about data file as the payload, essentially what's your real data content. The data file is for the same range of the data timestamp, so to speak. What is the deleted record? So it's more like holes. You say, those records are no longer in the system. So those are the content you build up. The way we build it up is we scan the log. When the log is still sitting in memory without going to the I/O yet, we'll scan the log. We'll populate all the checkpoint files along the way, the data and data. The data, again, is the content. Data is the deletion of the records. You don't have to watch the animation too closely, but you get the idea. So that's how we populate the content. So now you can imagine at the end of the day, it's almost like Swiss cheese, right? You have data and a lot of little holes, logical holes, and it's not very efficient. So that's where merge process come in. So it's almost like atom and particle and antiparticle. If they sit aside, you occupy twice the space, but you put them together, they disappear logically, right? So that's what the merge process is. So what we do is let's say in the middle, the range 200 to 400, you have a lot of records being deleted logically already. So we physically merge them as an offline process, and they just essentially reclaim the disk space, and also recovery will be faster too as a result. So you get the concept. It's a very simple concept. But this is also how we avoid random I/Os. We don't go in and update the content inside the file. It's accumulation at a certain point, append, accumulation, and then we sweep one more time and merge them, right? So very simple but effective design for I/O. So logging, just want to emphasize here, the log, if you have durability, is still going to be the size of the data change for your table. We can't get around it, right? If you want to have durability, you're changing data, we have to log that change somewhere. There is no, until we have NVRAM, right? That with DRAM, that's always going to be the case. So if your log is indeed the bottleneck today, you may have to think about getting the log device to be a better device. So this is an interesting thing because a lot of people, when they think about in-memory OLTP, they worry about the memory cost. But in the end, if you get 10x of the OLTP throughput, they end up spending more to pay for the storage to keep up the workload than the memory itself. So this is actually mind-boggling. The storage may be more costly than your memory if you want to have full durability. But the good news here is all the index operation is not logged. So it could significantly be less than today's disk traffic as a result. The recovery mode, all the recovery modes are supported. So how do we start up the database? How do we recover? Essentially, you load the data file, which is the deleted records as a filter, and then you stream the data through it, right, as a filtered map. And then we can do parallel recovery. Essentially, the recover is at the speed of the I/O device, roughly. So you can, rule of thumb, depends on the storage device, roughly 1 gigabyte per second on a decent server. But one thing I do have to call out is, unlike SQL Server today, let's say traditional SQL Server, which the recovery, after you do the undo, redo, et cetera, at the end of the log, you open up lazily, right? The database does not have to be loaded in memory. It's a lazy demand. So in other words, recovery of the database is not a function of the database size. However, in the in-memory OLTP situation, all the in-memory data has to be loaded in memory before we can open the database up. So this is important because you do have RTO impact. If you do a code crash recovery, your database won't be available until that data get piped in. Well, this is something you can get around with always-on, hot secondary standby, right? Because that data is always been warmed up in the memory, so you can do a fast switch over. But if you want to do a clustering solution, you do a cold start or a cold crash recovery, this is the overhead you have to consider. Okay, we talked about this a little bit. This is just a little bit more nuanced on the what's the factors that will benefit from in-memory OLTP more or less. But the essential principle here is, if you can move more business logic down to the database layer, the more you can benefit from this. So last one I want to show you really quick is the analysis and migration tool. So earlier on, when I did the demo for you, the graphical demo, how do I know which table to move? So there is a tool, what we call an analysis tool. You can set up with a data collector and monitor the production server remotely to say, let's watch this server and figure out which table is actually the bottleneck. And tell me, is this going to more likely benefit from in-memory OLTP? That's the y-axis. And how compatible it is with the in-memory OLTP. That's the x-axis. So, of course, the sweet spot is a lot of gain for very little work. So that's essentially the upper right quadrant. So the purchases table happens to be that one, and that's the one we migrated, right? So this is the tool to identify with your current workload today, what's the candidate to move. So the principle here is, that's really important here is, we don't force you to put the whole database in memory. So this is very different than a lot of other in-memory database out there, including SAP HANA, et cetera. They usually force you to move the whole database in as a unit. We allow you to identify the hot specific table and store procedure and do a la carte movement. This is actually a lot more friendly for the onboarding and also cost efficient, right? The rule of thumb we have seen with working with customers is you can have a 1 terabyte large database, but still most people have about 5 to 10% of the data that's really, really hot. So very rarely people have hot data all over the place uniformly. Usually it's concentrated to certain tables, a subset of the partitions, et cetera. So you have a way to reason and only optimize for that portion in a cost-efficient fashion. So the second part of migration, let me just show you something really very simple. Then we can end the talk and open up for Q&A. So I have here, I will just create a regular database. And I will skip this portion and simply create a table. Okay, so this is a SQL table, create an index. So I want to show you the migration wizard. By the way, that's the context. Create a store procedure and insert some rows. Okay. All right, so now I just have a simple database here. Did I create the table? Oh, I am, huh? Yeah. Yes, I am. Forgot this line. Sorry. Let me do it again. Won't be long. All right. So now we have a simple table with 4 columns, a index on it. And so now you can either do the manual way, or you can use what we give you as a little wizard called Memory Optimization Advisor. So it does a quick analysis on how compatible the table column types are. So there are indeed some incompatibility, such as lobs. It's not supporting the current version. We plan to support in the next version. There are very few, but there are indeed, lob is one of the prominent ones we're not supporting. And we don't support foreign key yet, and we don't support trigger. So there are things like that. It's not fully supported. So give you a little bit of warning, just say this is going to be schema bound once you do this, since build on top of it has to be changed. The next one, it detects you don't have that checkpoint file group pre-created, so it offers to create you that. So you don't even have to manually create that file group. So, and also it will rename the table to something called old, and you can also select to say copy the table to the new, copy the data to the new table. And then it identifies found the index, and it will try to migrate the index for you, and has a hash bucket size defined. And oh, that's the primary key. I'm sorry. Actually, this is the primary key for durable table. It has to have one, and then identify the index, try to duplicate the index. And at the end, it simply is this script, right? You can write it yourself. It's very relatively easy. You can see all the syntaxes we talked about, the concepts, or you can simply use the tool to do the migration. So it's a quite simple way to get started. Well, I'm 3 minutes ahead. I think I will skip the memory control demo. That one will run long, but the concept there, in case you wonder what it is, I want to show you how to do the calculation and show you that how to actually rate the memory cost, which you can simply go to the reports. There is a memory usage by memory optimized objects. So there is a nice report. You don't have to do calculation. You can just monitor it from the report. And then I want to show you the resource governor to control the memory. But you get the concept. There is a book online examples. You can just also you can just replay whatever I have in the notes section as well. So let's open up for Q&A. Thank you.